Hi, so hopefully you're ready to continue with some more considerations of the Prandtl number and dissipation, right? So continuing our discussion of the viscous dissipation for a flat plate, right? And we stopped at this equation, our expression that we got for the, so we said this R, which is the ratio of the thermal TAD minus T infinity by U infinity square by 2 Cp. So this ratio is basically something that I can calculate, right, as a function of this Prandtl number by solving this equation, right? And this is called the recovery factor. And for a flat plate, okay, the adiabatic wall temperature is constant, meaning it is independent of x, and hence it is also called eigentemperature. So this is where we stopped. Okay, let us continue from there. Okay, and now in this expression here in 13, okay, this U infinity square, right, by 2 Cp. Okay, now that is actually equal to T naught minus T infinity, right, which is essentially this, right, where T naught is basically total temperature of the outer flow, right, total temperature of the outer flow. And what this basically means is that the dimensionless, yeah, a rise in temperature of the adiabatic wall due to dissipation, right, is called the recovery factor. Yes, well, right. So basically, we are looking at the rise in temperature of the adiabatic wall temperature, and we are non-dimensionalizing it by this term in the denominator, and we are calling that as recovery factor. Okay. Now now let us see what this thing is, the thing that we wrote the bottom, the denominator rather. Okay. Now this delta T AD, I'm just denoting that as delta T AD, is essentially the increase in temperature here due to the adiabatic compression of an ideal gas at constant specific heat, right? This is the Cp, constant specific heat capacity. Okay, so now this thing actually, so this, okay, is the increase in temperature okay, due to adiabatic compression of a gas, okay, at constant specific heat capacity, that is Cp. Okay, so increase in temperature due to adiabatic compression of a gas at constant specific heat capacity, Cp, right. So of course, now at Prandtl number 1, right, the recovery factor is also equal to 1, right. So if from 13 basically I can see that which means this from it goes from 13 essentially minus T infinity is equal to this, right. So which means that the increase in the wall temperature, right, increase in the wall temperature due to viscous dissipation is equal to increase in the temperature due to adiabatic compression. It's exactly the same as so. Now, the thing is basically what we are doing here, if you see, right. Now, okay, let me write that down first. So, what this essentially means, that increase in the wall temperature right due to viscous dissipation is exactly equal to increase in the temperature okay, adiabatic compression. Okay. Now, so I'll give you some numbers and stuff. Now, the thing is that basically what you see is that the recovery factor, okay, so I am taking the temperature here, okay, the temperature difference of the adiabatic wall temperature with the free stream temperature, right, and this is we kind of trying to measure this in terms of the local velocity, right. And this also happens to be equal to the bottom. You can see here that this is actually it has no, this is basically the velocity, effect of the velocity, and that is also equal to this change in the temperature, right. So, this is the total temperature of the outer flow minus the free stream, right, and this is the adiabatic wall temperature minus. So, essentially what I am saying is that the recovery is adiabatic wall temperature minus the free stream by outer flow minus free stream, right. This is a recovery thing, and so this is the increase in temperature, okay. The numerator is the increase in temperature due to adiabatic due to viscous dissipation, okay, and this is the increase in temperature due to adiabatic compression of a gas at constant specific heat capacity. Okay. Now, some output from research, research. So, I can say basically, okay, so I've got Prandtl number and I've got the recovery factor. Okay. Now, this Prandtl number is less than 1, okay. The recovery factor is also less than 1, Prandtl number is larger than 1, recovery factor is also larger than 1. Okay. So, if you sort of look at this, yeah. So, for example, Prandtl number less than 1, recovery factor is less than 1, which means in the first case that the increase in temperature, right, due to viscous dissipation is less, right, than the increase in temperature due to adiabatic compression, right. So, due to, right, and that's because if the Prandtl number is less than 1. If Prandtl number is larger than 1, okay, the increase in temperature due to viscous dissipation is larger compared to the increase in temperature due to adiabatic compression of the gas. Okay. So, I will give you some values. This is from research, this is for your reference. Okay. For example, now values like this. So, R is equal to Prandtl number for very small Prandtl numbers, and this was given by Kirsten, H. Corner, this, right? And again, okay, this is for very large Prandtl numbers, okay, and this was given by okay. Now, what I'm going to do is now look at a plot which you can you can pull up the actual reference and sort of look at that, or you can this is I've got this from Schlichting's a book actually. So what I'm going to do is, okay, so look at this. Okay, I'm losing some. Okay, fine. So if you sort of look at this, okay. Now, if you look at this plot here, what you basically see here on the y-axis is okay, is the recovery factor. Okay, so TAD minus T infinity by infinity square by 2CP, and on the horizontal axis is essentially the Reynolds number. Okay, this is for the Reynolds number, and you can see that between this is the laminar zone, because this is between 0.5 million, 0.1 million to 5 million. So this region from this plot that you can see, now these are the data which has been plotted. Okay, now here, so this here, what you can see in the laminar region, the recovery factor is 0.85. Okay, and then this this corresponds to a Prandtl number of 0.72, and this experimental result actually agrees well with theory. Okay, so it is from this plot that you sort of can see that, and this is, like I said, the measurement of the adiabatic wall temperature of a flat plate at 0 incidence in air after Eckert and Weiss 1942. Okay, so and in theory Prandtl number is 0.72. Okay, so it overges well for that. Okay, so if I go back here, let me sort of write that down. This is just a note, so to speak. So I might as well just write that here, that in laminar region or in laminar flow, say, okay, that RE, right, is less than this. Okay, now the recovery is 0.85, right, and the corresponding Prandtl number is 0.72 here. So as the gist of the matter is that the experiment agrees well with theory. Okay, so having talked about that, now we will just sort of slowly look at okay, some wedge flows and how how the temperature profile or the temperature, and how exactly are we going to arrive at arrive at an expression for the temperature field in case of wedge flows. We've got wedge flows, we've got a wall jet, and we're going to talk about a little bit about the Usselt number. Okay, so now when we're going to talk about the next thing that we're going to talk about is wedge flows. So we basically use the equations that we have been use of similarity solutions that we've used earlier, right? And then solve that and get an expression for the wall temperature field, and that should give us an expression for the wall temperature, okay, which is our main purpose here, okay. So now if you remember right, so let us sort of do that, okay. Now okay, so now if I were to do that, so let's just do that, okay. So wedge flows, okay. Now so here we're going to write the velocity, right, in an exponential form from the x, and beta is this, right, and then we shall use the solutions. So following solutions, right, which is that, okay, then that okay, and of course we have an expression for eta, which we write as that this, right, which is equal to that. Okay, and then of course then of course we have right. So if I do this, then the equation that I get is so. So I get this equation, right. So if I use these solutions and so on and so forth, so the equation that I get is this. That, okay, and the corresponding boundary conditions. Okay, and eta very large is this, right? And then of course we solve this equation. We solve this equation for, we solve this, Prandtl number and m, okay. So then we get the recovery. So the recovery factor is a function of both PR, the Prandtl number at M, right? So we get, so we have to solve for the wall temperature definition, and then we get the wall temperature field actually, and then we get this. Okay. This. Right? Now it is interesting here that, so we get this expression. Now the only thing is that, you know, we have been able to, we have written the velocity like this, right? We write the velocity in terms of the x, right? Now if the increase in temperature due to dissipation is also related to the local velocity, right, which can be written in terms of x, right, raised to a certain power of m. Okay. So if this also is something that I could write, you know, in that fashion, then we can get an expression for the recovery factor, which is independent of x. What I mean is that if I were to write, okay, if I were to write this, okay, so if I were to write, okay, to this, right, then we will get, in, if I were to do that, then you get a recovery factor, okay, independent of x, independent of x. Okay. Now, so that becomes interesting. Okay, fine. So let us. So that's that about the, you know, that's that about the wedge flows. You know, if I were to write it like this, the next thing is let's talk about a wall jet. Okay, we'll talk about a wall jet. Okay, so here, so in wall jet, okay, well, right, it's actually proportional to the inverse of x, okay, and U max is proportional to the inverse of root x. Okay. Therefore, the recovery factor, which is a function of the Prandtl number, so the recovery factor based on the maximum U, okay, recovery factor based on the maximum U. So this term, as you can see here, so the numerator is a function of 1 by x, and the bottom actually is a function of you know, under 1 by under root x. So this is actually independent of x. The recovery factor actually is an right, independent of x. So that's very interesting. So of course, now for Prandtl number 1, recovery factor is 0, right. Now if for Prandtl number 1, in this case if Prandtl number 1 recovery factor is 0, which means that the adiabatic wall temperature is equal to the free stream temperature. Okay. So where we will just talk about the Nusselt number, and then we will stop. Okay. So let us do that. So let us talk about the Nusselt number. We haven't done that at all. So that should be the last thing we talk about, and then we will stop for this module. Okay. Right? Now, the accounting for dissipation, okay, if you account for dissipation, heat transfers, if you account for heat transfer, if we account for dissipation, now the heat transfer can occur only if the actual temperature of the wall is different, right, from the adiabatic wall temperature. So let me write that down. So if we account for viscous dissipation, so if we account for viscous dissipation, okay, so heat transfer can occur, okay, only, right, only if the actual wall temperature is, only if the actual wall temperature is different, okay, from the adiabatic wall temperature, okay. So if you account for viscous dissipation, right, so the heat transfer can actually occur only, right, if the actual wall temperature is different from the adiabatic wall temperature, correct, right. Now, so what we do here is that the energy equation is linear, okay. So now since the energy equation is linear, okay, so the two temperature fields, okay, one is due to the dissipation and other is due to the difference in the wall temperature and the adiabatic wall temperature, are superimposed on one another. Since it is linear, so temperature fields, right, due to dissipation, right, and due to temperature difference, right, are superimposed on each other. Okay, so if I do that, then we get a Nusselt number, something like this. Right? Now, if the wall temperature, right, if the wall temperature is greater than the free stream temperature and less than the adiabatic wall temperature, heat is transferred to the body. Heat is transferred to the body, okay, although its temperature is higher than that of the surroundings. Yes, well, this is like an interesting thing here. So now you see, now if you see here, if the wall, so basically like we said, that if you account for the viscous dissipation, heat transfer can occur only if the actual wall temperature is different from the adiabatic wall temperature, right? Now, if this is larger than the surroundings and less than the adiabatic wall temperature, okay, heat is transferred to the body. So so this is the wall temperature, which is less than the adiabatic wall temperature. So in this case, heat is transferred to the body, right? So even though its temperature, yeah, is higher than that of the surroundings. So just notice what I'm trying to say here. So this is the wall temperature, right? This is the wall temperature, which is larger. So this is the temperature of the wall, which is greater than that of the surroundings, right? However, the adiabatic wall temperature is larger than the wall temperature, okay, the actual wall temperature. And we said, if you account for viscous dissipation, okay, heat transfer can occur only if the actual wall temperature is different from the adiabatic wall temperature, which means that in this particular case it is so, right? So so due to the viscous dissipation, there is actually a difference in the actual wall temperature and the adiabatic wall temperature, and hence heat is transferred to the body, okay. The only catch is that heat is transferred to the body, although the body actually is the body's temperature is actually higher than that of the surroundings. Okay, so I think that's all I need to that's all I need to discuss about dissipation effects, and hopefully you get a picture of the interesting things happening here, and also along with the theory, hopefully you get an idea of how the math shapes up, so that we get information from the math also. And so this gives you an idea as to if we do take into account the viscous dissipation, then what transpires, and compared to if we don't, which is what we did for the most part before we started this one. So I am going to stop here, okay, and hopefully that you can make some head or tails out of this. Okay, so so I will stop here, and I think this is probably the close of this course. I hope you've picked up some things, okay, and I will try to answer as many questions as you may have, and hopefully I can answer some of them at least. Okay, so thanks.